Thank you. Okay, so sorry, just turned on the recording. We're doing special triangles right now. I'm trying to give you guys a heads up for Math 104 because about the first third of trigonometry is based on special right triangles. And so we're going to talk about them tonight, and then next week I'll kind of give you a really, really light introduction to trig and right triangles. Okay. But we started talking about what's called a 45, 45, 90 right triangle, or it's also called an isosceles right triangle. Okay, isosceles means two sides are the same, and we indicate that with tick marks there. Now, without proof, meaning I'm not going to boggle you with all the math that goes into it, all isosceles right triangles, the sides follow this pattern. If this is a 45, 45, 90, then, and I haven't figured out why, if this is side A, if this is A units long, and I don't know why everybody uses A, but they do, okay? The letter doesn't matter. This is A, because we talked about them being isosceles, so the two sides are the same. Okay, and this side is A times the square root of 2. Okay, that's a formula or a pattern that you just simply need to know. Okay, in an isosceles right triangle, okay, the pattern is A times the square root of 2. So, for example, I could say, what are the other legs if this is 5? If this is a, I have to tell you, whoops, I have to say this is a 45, 45, 90. Okay. And if this side is 5, what are the other legs? Well, because it's isosceles, this is 5. Okay, automatically, just whatever that is. And this is automatically 5 times the square root of 2. Okay, that's really all there is to it. I'm going to show you what causes stumbling for students, but that's basically it. That's the pattern that you have to know. For an isosceles right triangle, the pattern is A radical 2. The two legs are side A. The hypotenuse is A radical 2. Okay. Well, that seems pretty easy. So how can we screw you up? Of course we can. Well, what if I gave you an isosceles right triangle? Okay. By the way, do you guys know that the three angles of a triangle always must add up to 180 degrees? This angle, and this angle, and any triangle you make, the three angles have to add up to 180. Okay. There's some other facts that we'll get to. But what if I told you this was, okay, I'll be nice. What if I told you the hypotenuse is 8? The hypotenuse is 8. Okay, what are the other two sides? Can you go backwards? Okay, there's a bunch of ways students do this. I'll show you one way. Maybe you'll find a better shortcut, or maybe you'll see a pattern here. Okay, if you recall, let's go back. This problem that we just did a few minutes ago, I said this was 5. Okay, so this was 5, and this is 5 times the square root of 2. So going from side to hypotenuse is easy. You just multiply it by the square root of 2. Okay, but going from hypotenuse back to side is a little bit more complicated. Here's the way that most students have liked. I personally have a shorter way. But most students have said, this is a times the square root of 2. According to the pattern, the hypotenuse has to be a times the square root of 2. So something times the square root of 2 was worth 8, according to this pattern. Well, then solve that for a. Okay, we're going to divide both sides by the square root of 2. So that gives me 8 divided by the square root of 2 equals a. But we learned way back in chapter 8, or most of us did, Carmen didn't, that you can't have a radical in the denominator. So how do you rationalize it? Okay, do you remember that? We multiply top and bottom by radical 2. So that gave us 8 radical 2 over radical 4, because when you multiply, you go inside, whatever. But this ultimately reduces to 8 over 2 to become 4 radical 2 is a. Because this 4, square root of 4 becomes 2, 8 divided by 2 is 4. So let's go back and look at my work. If I gave you the hypotenuse and wanted to know what this other leg was, then you make up this equation out of thin air. You say the hypotenuse has to equal a times radical 2 because of that formula. The hypotenuse is a times radical 2. So then you just solve this equation, solve by dividing by radical 2, get a alone. But then you got to remember all the things about can't have a radical in the denominator, so you got to do all the rationalizing and simplifying. But the bottom line of all of this is now we figured out that this has to be 4 radical 2, and this has to be 4 radical 2 because they're both a. The two sides are the same. Yes or no? Okay. So let's have you guys.
Wait, you said A is 4 radical 2? Not
Yep. Not what?
Sorry, I'm looking at the back. So that means if you have 4 radical 2 times radical 2, it would equal 8.
Yep.
Reverse.
But
Okay.
it was a 2.
4 radical 2 times radical 2, okay, becomes 4 radical 4. Remember, because when you multiply with radicals, you go inside. So, but square root of 4 is 2, so this is 4 times 2, so this is 8.
I see it now. Okay.
So if this was 4 radical 2 and you multiplied it by radical 2, it would become worth 8, which is what that says.
Okay, I see it now.
Somebody else had a comment.
Oh, I was just wondering the same thing.
Are you okay? Did my answer satisfy you?
Yas.
Okay. Anybody else? That's the hardest thing. Going from leg to hypotenuse is easy. You just multiply it by radical 2. But going from hypotenuse back to leg, that's a little bit harder. Okay. And most students have used this technique of making a little baby equation and then solving this equation for a. And that's your 2 legs. So what if I gave you, okay, I'm going to draw it backwards this time, 45, 45, 90 this way. What if I told you that the hypotenuse was, I don't know, 14 radical 6? Can you find the 2 legs? So let's pause while you work on that. So I got that A was 14 radical 3. Now I'll show you how I got it in a minute. Okay. But if that's A because it's isosceles, because they're the same size, then they got to be the same. So what we said was the hypotenuse, 14 radical 6, has to meet this formula, has to be this. The hypotenuse is always something times the square root of 2. Okay, so then we divide both sides by the square root of 2. Now, one of the things we talked about, okay, was you could divide radicals inside. So this 2 goes into 6, 3, so this becomes 14 radical 3, and you're done. There's a harder way to do it, but that's the easy way. Okay, going back, if we had 18 radical 12 over, let's say 8 radical 3. Okay, we did something like this when we were back studying this. We said you can divide, you can reduce 18 and 8, that becomes 9 over 4. Those reduce, but then these also reduce. 3 goes into that 4 times. 3 cancels with 12 4 times, and then simplify the square root of 4 is 2, and you can go on from there. We're not done. But we said that way back in chapter 8. We can reduce outside, we can reduce inside. That was a quick way of working with radicals. Again, there's many other ways, but that's how I got that answer. Okay or not okay? All right. So that's one special right triangle. One of them.
Wait.
Ah, okay. I'm sorry.
Okay, I'm good.
Anybody else? No. Okay. So let's put that up. The first one is what's called 45, 45, 90. Okay. Degrees. Those are the degrees. It's called isosceles right triangle. And the word isosceles means the two sides are the same. And it fits the pattern of A times the radical 2. Okay, that's a leg, that's the hypotenuse. All right, so that's special triangle number 1. Now we're going to get to special triangle number 2. And it's called a 30, 60, 90 triangle. Okay, and it doesn't have any special name. But its pattern is A radical 3, 2A. I'll show this in a triangle. I'll show you this. That's its pattern that you need to know. Again, keep in mind, part of this is for our course this semester, but I'm trying to set you up for trigonometry. Either those of you take it in the summer or those of you take it in the fall. Okay, that's the pattern, A radical 3, 2. Now, what's that mean? Now, this is kind of important. On a 45, 45, 90 triangle, we could be really sloppy because two sides are A, who cares? And the hypotenuse is A radical 2. That was pretty easy, okay? You could be kind of sloppy and kind of lazy with this triangle. You have to be much more exacting on this triangle. So let me draw it for you. Okay, We got the right triangle here. Okay. The smallest angle is 30 degrees. Now, it could be at the top or it could be at the bottom. We'll worry about that in a minute. But the two angles, 90 degrees, 30 degrees, 60 degrees. Okay. Remember that the three angles have to add up to 180. They do. Now, here's the first catch. A is opposite the 30-degree angle. The smallest side of a triangle, the side, is always opposite the smallest angle. That's a truth from geometry. I don't know how many of you took it back in high school or whatever, but the smallest side, the shortest side, is always opposite from the smallest angle. The biggest side is always opposite from the biggest angle, 2A. So the hypotenuse is always double the short leg. The hypotenuse is double the short leg. And then the other side is A times the square root of 3. And it's opposite the 60-degree angle here. Okay. Too many arrows make it confusing, but the key to me is that the hypotenuse is always 2A, always, no matter how I draw it, no matter which way, okay, I draw it. If I tell you this is a 30, 60, 90 triangle, everything else, this is 2A. The hypotenuse, which is opposite the right angle, is always 2A. Always. That won't change. The short side, A, is always opposite the 30-degree angle. So if there's a 30-degree angle, then what's opposite from the 30-degree angle must be A. And then what's left is A times the square root of 3. Okay, that's the pattern, and it's real nitpicky. If you get those positions mixed up, if you put the A radical 3, and 2A in the wrong place, you put them opposite the wrong angle, then your whole triangle is screwed up. Nothing's right about it at all. So the hypotenuse is always 2A, always. That will never change, no matter how you twist a triangle. The A side is always opposite the 30 degrees, always. And then by default, A radical 3 is what's left over. But it will automatically be opposite the 60-degree angle. Okay, so how can we make this more confusing? Well, here we go. In my opinion, okay, the most important side is the A side. Okay, no matter what else they give you in the problem, like I gave you different sides and hypotenuses back up here when we did sample problems, your first step is to always get A. Okay, sometimes they'll give you A, sometimes they won't. So let's do some problems and talk ourselves through it, and hopefully you guys will ask some questions. Can I erase this formula? This triangle picture, at least.
I'm good.
Okay, we still have that formula up here. Okay, so here we go.
Does this one have a name? Like the other one was called Isosceles?
No, it does. No, it doesn't.
Okay.
Okay. The word isosceles is for any triangle. If two sides are the same, it turns out this could be 80 and this could be 80 and this could be 20. This is just a general old stupid triangle with two angles the same, so the two sides are the same. So this is also isosceles, but it's just not a right triangle. Okay, so isosceles refers to any triangle that has two sides that are the same. Okay, this was an isosceles right triangle. This is nothing. Actually, for a little bit of vocabulary, you don't need to know this at all, but have you ever heard the word scalene? Okay, a scalene triangle technically means no sides are equal. Just from geometry, don't worry about it. Okay, scalene is a geometry term that means no sides are equal. So all three sides of your triangle are of different lengths. All right, so let's go back to here. Suppose we'll start easy. Suppose I said that was my 30-degree angle. Okay, and this was 5. This side was 5. How big is the hypotenuse?
10.
10. So the hypotenuse is 10. Is that okay with everybody?
Yep.
All right. What about this leg over here?
5 square root of 3.
5 square root of 3. That's it. You're done. That easy. Because I gave you the 5. I gave you the A value. Well, what if, okay, we'll set up another one, 30 degrees here. What if I told you this was 12? And I wanted the other two sides. Okay. What I told you was the key to everything is the A side. Find it first. Once you have the A side, you can find everything else. So how is the hypotenuse related to the A side? How are those two related to each other?
Double.
Okay, so the
two.
hypotenuse is double, times by 2. So we could write ourselves a baby equation. We could say 12 is 2A. 2A. Divide by 2, 6 is A. So this is 6. Okay, so out of thin air, I made that equation up. I said the hypotenuse, the 2A represents the hypotenuse. Okay, so out of thin air, I made up this equation. The hypotenuse equals the formula 2A. Solve that by dividing by 2, and we get 6 equals A. Now, if we know that this is 6, what is this side over here? Anybody?
6 radical 3.
Yep, that's it. It's always A times the square root of 3, A 6 radical 3. Now, I absolutely, fully accept that people could go from 12 to 6 in your head. Because if you go from A to that, you double it, well, then go backwards, you divide by 2. So I fully accept that. I show you this only to show you that there is a way to calculate it, okay, if you want to write a baby equation. But you can get backwards. You can do that in your head. So what if, oh, I'm gonna play with your brains here. I'm gonna put the 30 degrees here. Okay. And I'm gonna call this, how bad do I want to mess with you? I'm gonna call this 9. And I want the other two sides. So I'm going to pause right now and let you think about it. I'll work this out. This suddenly went from okay to, yeah, a little bit tricky. So I'll pause while you guys work on that. Okay. For what it's worth, I tried this in my head. Well, I don't want to show you how stupid I am. All right. So this is side 9, but what side is it in the pattern? Isn't this the A radical 3 side? Where's my glare? Yeah. So this is 9 is A times the square root of 3. This side that I gave you is technically opposite the 60-degree angle. Okay. So it must be the A radical 3. So 9 is the A radical 3 side. Okay. Divide by both sides by radical 3. Okay. Rationalize the denominator, make it look pretty. So we're going to multiply by radical 3 to do that. That gives me 9 radical 3 on top over square root of 9 on bottom. Clean this up a little bit more, and I'll show you if you want me to, but I got 3 radical 3 for the A side. And remember, the A side is always opposite the 30-degree angle. Now, I didn't do all my work. I said the square root of 9 is 3, but 3 divides into 9 3 times. That's how I got there. Okay. The hypotenuse is 2 times this. So the hypotenuse is 2 times 3 radical 3. The hypotenuse is 2 times the short leg. So the hypotenuse should be 6 radical 3. And again, whether you show me this work or you can do it in your head, that's up to you. Questions? Big question. Did I start the recording? Yes. You want to try one more of those?
Sure.
Okay. So let's erase this one.
Professor, I got a question.
Okay.
So A is 3 radical 3?
Yes, in this case. Well, because that reduces to 3 radical 3. I didn't finish it here. I finished it in my head and wrote it up here.
Right. Okay, I see it now. Sorry, I got it.
That's okay.
Thank you.
Okay, anybody else? Okay.
It wouldn't
So-
just be 3? Oh, gosh.
Say again. Okay.
Oh.
What's the matter? So from here, this becomes 9 radical 3 over 3, because the square root of 9 is normal 3.
Oh,
But then
okay.
the 9 and the 3 reduce to 3 radical 3, and that's what I put over here.
I see. I got that. Sorry. Got it.
It's okay. No, don't be sorry. Okay. It's okay. I mean, we're doing a lot of stuff. This, by the way, is one of the reasons I like to teach this, not just to give you guys a little heads up into trigonometry, but this is kind of a cool review of your radicals, which will be on the final exam. Now, it's not a complete review, but at least it gets you thinking about them a little bit more. So that's what I like. Okay, let's see. How can I? All right, we'll do this one. I'll twist my triangle even worser. There's my 90-degree angle. There's my 30-degree angle. And I'm going to tell you that this side is 21. And I want you to find the other 2 sides. So we'll pause while you get. Okay, so I put the answers up here, and then I'll go through the work and the explanation. But doing the work, I got the A side was 7 radical 3, and the hypotenuse was 2 times that, so it was 14 radical 3. Okay, so let's do the math and see how I got those. This is the side opposite the 60-degree angle. If this was 30, then this had to be the 60 up here. So this is opposite the 60. So it was the A radical 3 side. So 21 equals A radical 3. So you divide both sides by radical 3. Okay. So then you rationalize. So that means you multiply top and bottom by radical 3. And you get 21 radical 3 over radical 9 equals A. But radical 9 is normal 3, so you get 21 radical 3 over normal 3. And 21 radical 3 divided by 3 is that. And then I just multiplied it by 2 to get to that. On the test, there will be just a couple of these. Okay. And the amount of work you show me or don't show me doesn't matter. Again, I fully accept that some of you guys can do this work totally in your head, and others of you want to see an equation and want to work through it. Great. Okay, whichever. All I'm going to do is grade the fact that you got the sides or you didn't get the sides. Any questions? Okay. There was a worksheet I suggested the other day that you download. It's on Canvas. It's in the Chapter 11 module that says Special Right Triangle Worksheet. It's just got a whole bunch of these triangles all over it and asks you to find all the missing sides. And I believe the answers are on the worksheet also. So you can try them and check your own work, and then come back and ask questions on Tuesday and Wednesday. Okay, couple questions like this on the test. Couple questions where, well, like this. I'll give you some more practice on Monday or Tuesday, Wednesday. All right, I want to erase the board, go on to a new topic. Are we okay? Okay, remember Tuesday and Wednesday, I'm going to show you how this has strong relationships to what you're going to start learning in trigonometry. Okay, so can I erase? No one's going to yell at me? All right. So the next topic that we're going to get into is chapter 11.5. I think it's 11.5. Yeah, 11.5. Okay. Systems. It's systems of conics. It says non-linear systems. And it kind of means almost the same thing. Don't worry about it. Suppose, let me get, Suppose I gave you this picture like this, a line, and I gave you this one, a parabola, and I asked you, where do they intersect? Well, on the picture, it's here and here, more or less. Okay, on the picture, it's here and here. But what if I gave you their equations? X plus y equals 4, and y equals x squared plus 2. See, if I gave you the picture, okay, and I drew it accurately enough, you could say, hey, they intersect here and here. Cool. But what if I gave you their equations instead? What if I give you the equations and said, where do they intersect? Well, if you think back, one of the things we learned in chapter, I believe it was 4, in solving systems, we could either solve by graphing, which sucks, or we could use substitution, or we could use something called addition, elimination. Okay. There were other techniques that I did not get into, but these were the main things. When we were trying to solve a system, first we started by graphing them, and we found out that nobody could graph. Okay, and it was slow and it wasn't very accurate, so everybody hates graphing. Okay, but then we introduced some more algebraic techniques. We said, we can use substitution, or we can use addition, elimination. Okay, we can do this a bunch of ways. So one of the things, that's what we're going to be doing in section 11.5, is we're going to be trying to solve a system of equations that aren't straight lines, that are conic sections in some way. And we're going to use primarily substitution or addition, elimination. That's going to be our goal. I can't give you a guaranteed thing that will say, when they look like this, always use substitution, or when they look this way, always use addition, elimination. It doesn't work that way. I can't. You need to practice the homework, okay? And just the rule of thumb is, if you make the problem uglier, you're on the wrong track. If you make the problem appear simpler, you're probably on the right track. That's all we can do. So I want to walk through this and show you. I'm going to use substitution, because I look here and I look at this top equation, and it says x plus y is 4, but y is the same as x squared plus 2. So I could rewrite this as x plus x squared plus 2 equals 4. Because what I'm doing is I'm replacing this y, I'm substituting this y for this thing, because the second equation tells me I can't. Okay, does that kind of make sense to everybody? Is that okay? Well, now the game is solve that equation. Okay, well, we have x squared plus x minus 2 equals 0. It was a power of 2, so I put it in order, x squared, then x, and then I subtracted 4 from both sides, so I got that. Okay. It turns out this factors, as a matter of fact, remember, you can use the quad formula if you want, but I would tell you that 99% of your power equations in this chapter will factor. They'll turn out pretty nice, most of them. Now, we all know mom is wacko, okay? But most of the problems will turn out nice. And I promise you on the test, the problems will turn out nice. So we factor this as x, that's going to be plus 2x minus 1 equals 0. And so we split x plus 2 equals 0, which means x is negative 2, or x minus 1 equals 0, which means x equals 1. Okay, now here's the catch. I hope you guys are all awake. Students at this point quit. They go, well, the answer is negative 2 and 1. Solution set negative 2 and 1, because Foster wants those stupid solution set things. Totally wrong. Totally wrong. Go back and think of a picture. If we had a parabola, okay, crossing with a line, whatever that line is, I don't know. Check it out. It has 2 points, but each point has an X and a Y in it. Each point where the parabola and the line cross has an X and a Y. That's what we're shooting for. Where do they intersect each other? Where do they cross each other? We've only found the X's. We need to find the Y's. So the way I have found over the years is after I get my X's, I say if X equals negative 2. Okay, then I plug it back into one of these. And I always try and pick the simplest one. So if X is negative 2, then I have negative 2 plus Y equals 4. Negative 2 plus Y equals 4. That tells me Y is 6. So if X is negative 2, they intersect at the point negative 2 comma 6. That's what that says. When X was negative 2, plugged it back into one of the equations, whichever, okay, and I get Y is 6. So there is a point of intersection. But what if X equals 1? Well, plug it back in again. Okay, if X is 1, then I have 1 plus Y equals 4. Plugged it into that one. So that means Y is worth 3. So this is the other point of intersection, which is 1, comma 3. So my solution set, the solutions are saying it intersects at negative 2, 6 and at 1, comma 3. Oops. That is my answer. It's the ordered pairs where they intersect. Not just the X's, but we also have to figure out what the Y's are. Okay. How's that? Questions before we do more problems? So you have to make up your mind. You have to look at it and decide, what's the best way to solve this problem? Should I use substitution? Should I use addition with elimination? Okay. I'm going to give you addition elimination problem in a second.
Will it always be 2 points? Sorry.
Oh, no, that's a good question. No.
So it will be like find the other point or so? Or like
Well, it would be find all the points of intersection. Think about this for a second. Let's say we had a circle here. And I told you this circle is being crossed or is being graphed with a line. Okay. How many possible intersection points could there be? Well, if the line went through it, it turns out there could be 2 answers. 2 points of intersection. If it went through it, can you think of another possibility? What if the line doesn't go through it? What if the line nicks it? Just sort of goes like this, bam, hits it once. Then it's possible that there's one answer, because there's only one point of intersection if that's the way the numbers showed up. Is there a third possibility? Can anybody see a third possibility?
No intersection.
No intersection at all. Yeah, it's possible that whoever the jerk was that made up the problem has the line going out here, and there's no intersection between the circle and the line, so there's no answers. So Vince, to answer your question, you have to kind of mentally be prepared for multiple answers, or one answer, or no answers.
For one answer or no answer, we will have to make sure to write reject, correct? Like if,
Well, your math will show up. Yeah, you probably have some rejection. You may not realize it, but you're asking a deep question here. We can't graph imaginary numbers. So if you happen to get an answer where you're doing all your algebra and you're working through this, okay, you're working through your algebra and you get x is 2i. Well, we don't know how to graph an imaginary answer. So this would be a reject. So if you were working through your stuff here, okay, and you got an imaginary answer, instead of I, you got, instead of 1, you got I. Well, then that whole thing is rejected, because graphing imaginaries doesn't exist, but we can certainly have multiple real number answers. Now, I'm not sure that's what you were asking me.
yeah, thank you.
Okay, all right. Anybody else?
Could
Yeah.
there ever be 3 intersections?
Oh, sure. Sure. Okay. What if we have a circle? Okay. And we'll watch this. I want to put a parabola here. You asked for 3 intersections. Well, what if I put a parabola just like this? What if just by some dumb luck, looks kind of like an ant, doesn't it? Ant-Man. Never mind. Okay. If by some dumb luck, the vertex was down here in these other 2 points, it's totally possible that a circle with a parabola could have 3 answers. Okay.
So
what about it? Go
would
ahead.
that make it a 3 by 3?
No, it would just have 3 answers.
But the
system would still only be a
Yeah.
2 by 2.
okay.
It'd be a 2 by 2 system, 2 equations like this, but it would just happen to have 3 answers.
Okay.
Okay. Think about this though, just to confuse you. Can anybody think of a way that a circle and a parabola could have 2 answers? If I drew a parabola on that circle or somewhere, how can I get 2 answers?
Like if the vertex of the parabola just goes inside the circle, just a little beep.
Something like that?
Yeah.
Yeah. Yes, 2 answers. And we could actually get 1 answer. Okay. What if the parabola went like that? Oops. What if they just touched at that one point? And yesterday, we talked about getting really, really wide parabolas. Remember, if the A value was a very small fraction on a parabola. So it's totally possible that you could have a really wide parabola and a circle. No answers. Okay. So the point is you guys got to believe in your algebra. You got to go nice and slow, double check your work, just be prepared for a bunch of answers. That's all I can tell you. So let's try another problem. Okay. New example here. Example number 2. System x squared plus y squared equals 4, and x squared minus y also equals 4. All right, just for fun, can you guys tell me what graph the top equation is? What conic section it represents?
Circle?
Circle. That's a circle whose radius is 2. Because both the x and the y are squared and they're both assumed positive. Can you tell me what conic section the bottom one is?
Parabola?
Because,
It has the one variable being squared?
right, a parabola, whether it's up, down, or sideways, only one of the variables is squared in a parabola. So we have here a circle intersecting a parabola. Okay. I'm going to do this. You may see it a different way. I'm going to show you the substitution, no, excuse me, addition elimination way, just because I want to remind you. I'm going to take this bottom equation and multiply it by -1. That's going to give me x squared plus y squared equals 4, and negative x squared plus y equals -4. Because remember, the elimination technique was multiply by some magic number so that when you add them together, a variable drops out. And that required you to kind of think a couple steps into the future. I saw this as, oh, if I multiply this by -1, I'll have negative x squared. And if I add it with positive x squared, those will drop out. Those will cancel each other out. It could have been done an entirely different way. I just wanted to show this. So now, if we add these, my x squareds drop out. Important question. Can I add these two? Look where I'm pointing. Can those
Would it
two be
Be
added
y
together?
cubed?
Would it?
I don't know. No, it wouldn't.
Okay. Well, Carmen's, never mind. Okay, the answer is no, you can't add these. Because remember, in a problem, if you had x squared plus x plus 7, you can't call this x cubed plus 7. These to be able to add, you have to have like terms. They have to be exactly the same to be able to add these two together. Okay, so what we say is, I'm going to add these, but I'm going to recognize that I can't add those two. I can add these x squareds and they cancel each other out. I can try and add these, but they're not like terms. So the best I can do is write that and say, I tried, but I knew I couldn't do it. And 4 and -4 make 0. Okay, well, now we've got a much simpler problem. So we're going to factor out a y. Split it up. So either y equals 0 or y equals -1. Those are my two answers. Y equals 0, y equals -1. Okay, here it comes. Okay. Can I erase this or this first equation, system of equations up here? Anybody need it? All right. So again, if y equals 0, so we're going to set this up. If y equals 0, I don't know, maybe the bottom one. Always plug it back into one of the originals, and it doesn't really matter which one. Which one do you guys want to plug it into? The bottom or the top? Doesn't matter. Okay, I'm going to go to the bottom one. Okay, so then we have x squared minus 0 equals 4, because I plugged it into here, which tells me x squared equals 4. Now remember, hold on, this is where we come back. You're going to square root both sides, so you're going to get x equals plus or minus the square root of 4, which is 2. Okay, so, okay, where's my glare? There it is. In my solution set, remember the solution set is the group of all of your answers. And you put them down once, one big giant group of answers. Okay, I could have 2, 0, or I could have -2, 0. Those are two answers. When y was 0, x was those two. Okay, so there's two answers. Well, go for the other one. What if y was -1? If y equals -1. Okay, let's plug it back in. Then x squared minus a -1 equals 4. Okay, that's plus, so take it away. So I get x squared equals 3. Okay, again, square root both sides, but the square root of 3 is ugly. So we just say x is plus or minus the square root of 3. So now what do I have? When y was -1, x was positive and negative square root of 3, which tells me my answers are square root of 3, comma, -1, or negative square root of 3, -1. Closed solution. So this had 4 different answers for a circle and a parabola of some form. It had 4 different places where they all intersected each other.
Professor, didn't
Yeah,
didn't you show us at one point in one of those chapters that we could do positive or negative for one of those pairs?
yes. So
Or
if you prefer to write this as plus or minus 2, comma, 0, you can. And if you prefer to write this as plus or minus radical 3, comma, -1, you can. And then put those in your solution set instead. Yeah, a little bit easier. But I'm trying to reinforce the concept of 4 answers. If you want to use the little shortcut here, great, go for it.
correct, thank you.
Yeah. So I wanted to show you the addition elimination method. Okay, so I multiplied the bottom equation by -1, so that when I added these two together, the x squareds dropped out. I had to figure out how to add y squared and y, and I figured out I couldn't, so I just said that's the best I can do. Then I factored it and got 2 y answers. Then I have to say, okay, if y, one of my answers was 0, what does that imply the x was? Got to do a little bit of algebra there. if one of my y answers was -1, what does that imply x was? A little bit of algebra. I got 4 possible answers. Any questions? Okay. We'll do more of these on Monday. What do I want to do? Okay, let's set you guys up and have you guys try one more. Okay, I'm going to erase this over here. Let's see how you guys do with this one. This is a system of y equals square root of x and x squared plus y squared equals 20. Okay. Bottom one's a circle. For what it's worth, the square root of x looks something like that. Don't worry about it. Okay. Top one is a square root graph. Bottom one is a circle. Probably only one point of intersection. But let your algebra guide you. Okay, let your algebra guide you. So I'll pause it while you guys try and do the algebra for figuring out where these go. Are you going to use substitution? Okay, here we go. I personally would use substitution. Okay, I take this and put it here because that's going to give me x squared plus the square root of x quantity squared, because it says take y and square it. But if y is the square root of x, I'm doing square root of x squared equals 20. So I get x squared plus x minus 20 equals 0. I know that because it's a power equation, x squared, it's got to equal 0, so I can do all that factoring stuff. Okay. You guys okay with me so far? Any concerns? All right. Factors is x plus 5, x minus 4 equals 0. So this gives me x equals -5 or x equals 4. Okay, now plug it back in. Always the simplest one, if you can. So this is going to say if x is -5, then y equals the square root of -5, which means y equals I times the square root of 5. But this is imaginary, or it's complex, okay? We can't graph imaginaries. So this is a reject. This is a reject. We don't know how to graph yet imaginary numbers. You learn that in pre-calculus, math 141 or something, okay? So when x was -5, y turned out to be imaginary, but we don't know how to graph that, so we reject it. Okay, so over here, if x is 4, y equals the square root of 4, so y equals 2. Cool. So the solution set is the parentheses 4, 2, because this side got rejected. Yes or no? Yeah.
Yes. As soon as I saw that it was radical -5, I didn't pull out the I just stopped there.
You don't
Is
have
that
to. You
okay?
can just stop. Yeah, that's fine.
Okay, thank you.
Yeah. There's part of me that wants to show you all of the algebra because I want to remind you of all of the steps. That's the teacher part of me. Okay. But if you recognize that that's going to be imaginary and you go reject, then cool, you're done. You've seen it anyway. Anybody else? Okay, the only thing I can tell you is it gonna take some practice to do these in section wherever we're in 11.5. Yeah, because every single problem has a little trick to it, has a little twist to it. You never know, are you going to use substitution or additional elimination? You never know if somebody's going to reject or not reject. So the only way is to get in and do these problems. Now, I'm going to be available over the weekend to answer questions. I think Ann has been available. So I'll be more than happy. I've helped several people. They can't do a problem. I've done it, scanned it in, and emailed it to people so they can kind of figure out what my steps are. But the only way to do these is by practicing and practicing. Okay, there's no one trick that fixes everybody in this one. All right, I need to erase and move on to the last topic of the evening. Any questions? Okay, cool. Nobody's going to yell at me and say I need to take a picture. Okay. Okay. Well, how many people are here? Most people. Okay. On Tuesday, I might be late. Okay. Got some personal medical problems that we got to deal with, not me, but other people in my family. So have to take them to the hospital, get a little bit of surgery. I might be coming in late. We need more information from the doctor about how late it is. I might be contacting Ann and asking her to run the start of class on Tuesday, or I just might be late. So don't give up on me. I will keep you guys informed of everything that's happening. Okay, but we will have a class Tuesday because I do want to review and I do want to show you how a lot of this conic and special triangle stuff applies to trigonometry. But I will be late, so don't quit on me. And I will record everything I do on Tuesday so that even if you come in late, you can still see it or you can ask me questions. Okay, I got that. Now, the last thing I want to talk about is chapter 11.4, and they're called hyperbolas. Okay. And I've got some real mixed feelings about them. Yes, I need to teach them because they're part of the conic sections. They are there. They're a part. But most math courses that I've seen don't use them very often at all. I mean, you know, maybe once or twice in calculus, whatever. So I'm sitting there, I'm torn between, okay, well, how much should I do it? The other thing is they get really complicated really fast. So I want to keep it, I need to introduce it to you, but I'm going to keep it as simple as I can. As simple as I can. Okay, and I need to show you how mom expects you to graph these. And I'm going to promise no more than one question on the exam about hyperbolas. No more than one, so don't panic. All right, first question, or first idea. The formula for a hyperbola looks like this. X minus h quantity squared over a squared minus y minus k quantity squared over b squared equals 1. Or it looks like this. y minus k squared over a squared minus x minus h quantity squared over b squared equals 1. Okay, there are two forms for hyperbolas. Okay, a couple things before we talk about the similarities and differences. What does this look like? What if you just glanced at this and didn't think real carefully, what does it kind of look like? What formula? Nobody?
The ellipse.
What? The ellipse, good. Okay, if we come back, if you go back and you review the ellipse, it was x minus h squared over a squared plus y minus k squared over b squared equals 1. So the ellipse and the hyperbola look a lot alike, but the fundamental difference is an ellipse has a plus sign in the middle. Okay, and in the hyperbola, okay, there's always a minus sign. And that makes the whole problem just horrid. So that's the first thing. Now, we still know HK is going to be the center of this shape. But what shape? Well, again, I told you it's going to get confusing. Hyperbola has, okay, two branches. Two branches. If x comes first in the hyperbola, if your x is a positive and your y is the negative, remember this is minus this quantity. If x comes first and y is negative, it will look like this. Your hyperbola will look like this. It opens in the x direction. Remember, this is the x-axis. So if x is positive and y is negative, it opens in the x direction. And there are asymptotes like that act as boundary lines. So the hyperbola will come really close to those asymptotes, but never touch it. Okay, it won't go inside. It'll be a nice smooth curve. So a couple things. The basic shape of a hyperbola, it has what we call two branches. Okay, two branches. And they're defined by the asymptote. They come real close to the asymptote as each branch continues, but they never quite touch that asymptote. And I'll talk more about that asymptote in a minute. Okay. So this was sideways, two branches opening sideways because x was positive and y was negative. Well, wait, what if we reverse this? What if y is the positive and x is the negative? Take a wild, crazy guess which way the two branches are going to go.
Up and down.
Up and down. Yeah. If y is positive and x is negative, this sucker is going to go up and down, up and down. It's going to go in the y direction. Okay. And we will still have the asymptotes like that, acting as kind of guidelines. And I should have drawn this a little bit because it does come close to the asymptotes. Should have drawn it like that. Yeah, okay. So those are your two basic hyperbolas. Either your hyperbola is going to go sideways, or your hyperbola is going to go up and down. Hyperbolas will always have two branches, always. But how you draw them, where you draw them, depends on who was positive and who was negative in your formula.
So, wait, which one was which again?
When X is positive, you know what, by looking at this equation, do you know what I mean by X is positive?
Yes.
Okay, when X is positive, it opens in the X direction. Remember, X is sideways. When Y is positive, it opens in the Y direction.
Okay, that makes sense. Thank you.
Yeah, but does it make sense to everybody else?
So it just makes, so you just need to look at the first equation basically, right? From each one. So like X, the top one,
Yeah.
X minus H, it's a positive
Yeah.
X.
Right,
Basically, right?
and or yeah, yes, basically to know which way it goes. Now I got to show you how to do it on Mom, but that's the first thing, because Mom is going to ask you to pick which graph it is. When you graph this, Mom is going to say, okay, she's going to have buttons here, okay, and she'll have this button, or she'll have this button, or she'll have this button, or she'll have this button, a parabola, okay, or something like that. And so when you try to graph these on Mom, the first thing you're going to do is select which graph is it going to be. And that means you have to come back here and look at this equation and go, oh, it's a hyperbola because it's got a minus, but it's a sideways hyperbola, okay, because the X is positive, so it's going to go in the X direction, the two branches. That's the thinking that you have to go through. I just said a lot of junk there. Is that okay with everybody? Okay, so I need to kind of erase this and actually give you a real problem that we could do on Mom. So
Professor.
yes.
So we should kind of have a cheat sheet for all these formulas, huh? And
Basically, yeah. Yeah, because they're all similar, but they all have enough differences in them that it's easy to get confused. Yes.
makes sense.
Okay. Can I erase my drawings and my formulas for everybody? All right. Oh, am I? Please, God, tell me I'm
Yes, you're recording.
okay. Wow. Okay. Where does it show on yours? Mine doesn't show me I'm recording. Does it show on yours?
The top
Yeah, on the
left.
top left.
Yeah, mine doesn't show that. Oh, well. Okay. So let's take a simple problem. X minus 2 quantity squared over, oh, I'd say 5 squared, minus y plus 1 quantity squared over 10 squared. Now, let's call it 9 squared, just because it's different, equals 1. Okay, so what do we know? First off, we know it's a hyperbola. Which direction is it going to go? Just by glancing at it.
The sides. not the top.
Sideways. So we know it's going to be a sideways one. So that's what we're going to pick on Mom. We're going to click on that. Okay. What is its center? Even though we don't know what the heck a center is, what is its center?
2, -1.
Good.
Mhm.
2, -1. Is that okay for everybody? I mean, we don't know what the center of a hyperbola looks like right now, but okay, it's going to be that HK again. The same HK keeps coming up over and over and over.
But the signs would be flipped. Sorry, I don't remember that part.
Remember, when it's inside the parentheses, we take the opposite of what we see.
Okay.
Okay, you see a -2, we use a +2. We see a +1, we use a -1. when you're taking information out of parentheses, you're using a shortcut. Well, the shortcut makes it faster. The disadvantage is you have to learn the trick. Okay, when you take information out of a parenthesis like we're doing, you use the opposite of what common sense says. You see -2, you use +2. You see +1, you pull it out and use -1. Okay, now, in an ellipse, we talked about the X radius. So I'm going to use that. Mom doesn't use that vocabulary, but don't worry about it. The X radius is going to be 5. The Y radius is going to be 9. Okay, here we go. On Mom, we're going to click the button that says pick a sideways hyperbola. Bingo. Then you're going to find the center, 2, -1. Okay. Now, here's the catch. Mom is suddenly going to draw some asymptotes. What you want to do is go over 5. Let me get my red pen. You want to go over 5, up 9, and you want to control those asymptotes. You're going to have to do that with your mouse. So whatever this point is, if I go over 5, up 9, where is this point? Actually, 9 is up here higher. If I go to the right 5, right, and up 9, where is this new point?
7, 9.
7,
7,
8.
8.
7, 8. Okay, 7, 8. Well, so you're going to use your mouse and you're going to control the asymptote until it's going to go through here and here. At that point, okay, Mom, you'll click something and Mom will put in all of the asymptotes, okay, and Mom will draw the sideways hyperbola based upon your asymptotes. So the asymptotes control everything. So you've got to select the correct shape, sideways hyperbola, identify the center, and then from the center, you got to tell Mom, I'm going over 5, up 9, and that's going to create my asymptote. Mom will then draw everything in. And if you went over 5, up 9 correctly, over 5, up 9, to the right point there, the correct point, okay, it'll draw in the asymptotes, it'll draw in your hyperbola, and you're done. That's it. So you're using the X radius and Y radius just about the way we used it on an ellipse. It tells us to go over and up. Kind of okay?
What does the center do for it?
It just establishes where is this shape. Okay.
Never mind, dumb question. I get it.
Okay. All right. No, it wasn't a dumb question. We're talking a lot of graph theory. Okay. And I'm kind of coming in the middle of this. So it's a good question. Can you guys think about this just a second? This is a follow on Vince's question, which is really good. What if I gave you this problem? X plus 5 squared over 5 squared minus y minus 3 squared over 9 squared equals 1. Let me clean up my handwriting here. Okay. So I'm not going to do this one, but I'm going to talk about it. X minus 5 squared over 5 squared minus y minus 3 squared over 9 squared equals 1. Now, think about if we sketched this graph, how would it be similar? How would it be different than this graph?
It would be up and down, correct?
No, it's still got X, so it'd still be sideways. X is positive, so it's still sideways. Okay. Where would its center be? Where would the center for this shape be?
-5 and +3.
Negative 5, 3. Where the heck is negative 5, 3? Oh, negative 5, 3. Okay. Negative 5, 3. But hey, check this one out. The X radius and the Y radius are the same. So graph theory, math theory, this hyperbola would be identical to this hyperbola. They both open sideways. They both have the correct asymptotes, except this hyperbola is just shifted up here. That's what the center does. It takes this hyperbola and moves it over here. It's the X radius and Y radius that create the asymptote that really create the shape. If you could pick this one up and lay it on top of this one, they would be identical. They would be exactly the same. So the only difference is the center shifted this away. These two are exactly the same shape, same everything, except their centers are in a slightly different place in space. So, Vince, that was kind of a long-winded answer for your question, but your question was deeper than you thought it was. It required quite a bit of discussion there. It was a good question.
Second
Okay.
question.
All right, go ahead.
What did you say make it up and down? I kind of got confused. Just if the equation is plus or if the X?
Okay, if the X is positive, notice in this problem, X is positive, Y is negative. It always, because X is positive, it will open in the X direction, X meaning sideways. Okay. If I gave you this equation, what if I gave you y minus 1 squared over 2 squared minus x plus 1 squared over, I don't know, something stupid, 11 squared equals 1. I'm not going to graph this one. I'm not going to do it. But notice y is positive, x is negative because of that negative sign there. Then this one will open up and down because y is the positive value.
Gotcha. Thank you.
Okay. I know it's all new to everybody. Is that okay with everybody or not? Okay. I'm done. Finished. I'm going to stop recording. I'm done. I hope you guys do your homework over the weekend and come back on Tuesday. Remember, I might be a little